It's changed a lot. I mean, I was writing in raw C back then, you know, managing it just out of arrays.
Yes. And the first homework assignment was to find, like just now we just look at the threshold problem, and that took about 2 hours to run on our machine.
Well, my first computer vision was part of an AI class, so it was only 1/3 of the class. But
Sony.
it was back in very primitive days and
Hopefully it's still left.
primitive equipment.
Don't change hardware when you demo on Revit, please. That's my advice to you to tell me. Leave the analog computer, don't touch it. The day before the demo.
So where did you plug in?
Yeah, I did. But I think so.
Yeah.
That shot and little noise. That's okay. Okay. So the first thing we do is that using this calculator, I want to create a just a blank image, okay? And the next thing I'll do is let's see if I can remember the equations. Let's see if it works. I don't know. Okay, so just now we're working on RGB. Now we're working on HSV. HSV for some artists probably they're more familiar because actually that's how you select color in HSV space. And let me show you what HSV is. So if you move the cursor here, you see the RGB value is 255, 156.0. The HSV value is 0.055, for example, for the H, and then the SMV is 1. Okay. The reason why the saturation and the value is 1 because I set it to 1 right now. I can actually set it so that it actually gradually changes color. So from bright to light. Let me see if I can do that real quick here. Let's see if it does anything. I'm not sure. It's probably not going to do it. Why? Okay. Let's see. 50. Yeah, okay. It changed the value here. So the Y is basically increased from the 0 from the bottom to the top here, 255. So Y is actually getting more and more. So it's brighter on this side than on this side, on the top side. The reason is because the expression Y divided by 255 give you the sort of gradient across the image. Okay?
So when you put at the beginning of the statement HSV, that told it what kind of window to throw up, what kind of form to display.
What kind of yes, what kind of space we're working with.
Okay.
And HSV is not only one form that you probably will encounter. There's actually something called the YGBGR. I can't remember what this that five-letter thing.
CMYK.
And there's the one lab.
Cyan, magenta, yellow,
yeah,
and black.
You know that one. Yeah.
Yeah.
That one used a lot in sometimes robotic also. And the other one is the LAB lab. It's a new thing. So anyway, so when you get into OpenCV 2, you know a lot. You learn a lot of theory very quickly because there's just a lot of stuff that pack into the API. That's why I say if you're a casual computer vision guy, you're not really interested, you want to use it, that kind of overwhelms you because it's just so much information that you don't care about. You just want to know how to find the blob, you know? Why you care about all these things about gradients and Laplacian.
So if you just want to find a blob, then you use RoboRealm?
Yeah, use RoboRealm, or even, I think in my opinion, just use the processing. Processing has a lot of wrapper around this stuff.
Okay.
It's much user-friendly, it's toward the artist, and you know, it's much easier to use. I mean, you can code something up, you know, tracking a blob in less than 2 hours. Whereas here, it probably take you a while to get to it.
You say using processing with OpenCV? Or just
processing already contain OpenCV library.
Oh, okay. So you don't even
when you load, I mean, I think you have to load a few things, a few jobs.
Okay.
once you have the draw file in the, you probably have to install minimum OpenCV library to get it to work with processing. Processing, that I don't think distribution comes with the OpenCV stuff. So if I remember correctly, I done this 2 years ago for my robot. And that installation basically takes just a few jar files. And then there's a thing on top of a very thin layer. It's basically a JNI, the native call to the C code actually, not C++ at that time. So if you look at the code, it's actually just wrapped around all the OpenCV call. And then it does some stuff in Java to find all the blobs and figure out which blobs the biggest and things like that. But it's not very robust. The problem with processing, doing some of the stuff is that it doesn't expose the parameter to use, all the parameters. There's just tons of parameters in all these algorithms. And if you look at every paper has the tuning parameters that you have to work with. And in order to understand the pro and con of each parameters, you have to play with it, right? And it's very hard to capture that in a sort of high-level thing for a general purpose usage. Because every application is different. So last time in the contest when I tuned my robot at home, it's working fine. When I came here, everything's not working anymore because the lighting condition, everything, the shadow and all these things, throw that thing away. And it's always like that. And for most people that work on computer vision knows that the environment is so critical. Lighting, any kind of ambient light is hostile to you. It's like a hostile environment.
The hardest thing to do is to overcome shadowing, lights.
Yeah, this is why you see the robot contest a lot of time. They just they have a very sort of confined space, you know, with the green, very bright green, you know, black, white, very distinct value. So you don't have to do all this issue because then the segmentation problem is much easier. Okay. So I just for the last one, I just want to throw this out there. Don't ask me how this works. So I just got this question. I don't even remember all of it. I think this is so mod is the modulus for people that know number theory, or just in C is a percent sign. So what do you think is going to happen? Let's see if this works. Doesn't work. It's just like the way I expected. Anyway. When I try it at home, it looks very different. So let me see if I got the equation wrong. So basically, it's doing some kind of remapping of what the.
So you can't like revert, do an edit, and you have to reopen the image.
Yeah, this software is kind of like an academic software.
Yeah.
But it's a good book. But not recommended for this, for robotics. Anyway, I'll fix this next time. I'll show you next time. Okay, so we're gonna basically go back to the top OpenCV. So the reason why we kind of went over that stuff is because just to kind of give you an idea how to manipulate stuff without a lot of code, because otherwise you kind of get lost. Now that once we get that, now we can look at the OpenCV2 code. Actually, this thing doesn't do the edge detection. I'm sorry. So basically, this code just does one thing. I'm sorry, it's kind of go back and forth because I have the screen. I have the virtual environment, so I can switch back and forth very quickly. So let me just kind of show you the code for this. So this is the code. The first part of this code is just kind of read a file through the argument 1. It's just straight standard C++ or just C stuff. And if you cannot find an image, or cannot load it, then just cannot read image and return -1. And the next thing is, you see this a lot in the OpenCV code, is that there's a thing called name window. The name window basically does is that sort of kind of name a window, so you can put something there. Then you can then display your stuff to the particular window by providing the name of the window and an object to your image. And then you can perform the operation CVD color to convert the image to gray. And here we kind of tell it to perform this operation BGR to gray. So the image we load in earlier was BGR, not RGB, and then we convert it to gray color. So this is basically what we've done in the calculator, but in a code form, the API form. And then after that, you show the image there. Okay. The wait key 0, just say that basically wait for a key to hit, and then you exit. So this is a very standard code in the so if you just run it, you get an error because there's no image, and it's trying to basically load some stuff. You see a lot in this kind of stuff in the OpenCV. Sometimes the samples are not quite explained properly. But they did a good job, but they had a lot of samples. So I'm just saying they're probably hard to keep track of all the, I mean, most of the users are probably expert C++, they don't care about this little minor, they will probably read the code if they can't figure out. So this is basically what we had done earlier. So we show the original pictures and we have the break. Somehow my image is dead. Let's see. Okay. I have to kill images. Okay. So, and probably can I have to kill this too. Okay. So we just look at a very simple piece of code that invoked this method called CVT color. So in some books you will see something like CV : CVT color. So don't be alarmed if you see that. The reason you see that is because they don't use the namespace CV. And I think if you program C#, you probably know this already, which is namespace usage. So you simplify the code so that you don't have to keep saying what namespace this method is coming from. So they also allow you to have the same method with the same name coming from different classes and things like that. So this stuff is C++ stuff, so I'm not going to get into it too much. So earlier you asked me a question about data structure, right? So we'll kind of get into it here. The data structure is basically called MAT, M-A-T. So for example, here you got two declarations, okay? MAT A and C, and A is equal to whatever file you read in. Okay, so this is telling you to load as an image, as a color. Then here you got another usage of the constructor, which basically use a copy constructor. And I don't think this actually copy the data. In the new in this OpenCV 2.4, a lot of time, even you set something to something like you assign C to A, doesn't mean that two copy the data. It actually means one copy. It's a shallow copy. So you only copy the headers, it doesn't copy the data. The reason is because so that you don't have all this extra copy hanging around, and then memory-wise, you have to manage. They manage everything for you because they have this intelligent reference count pointer, so they know when this object's no use anymore. So this is a very nice feature that C doesn't have compared to the version 1. So here, there's another usage here let's say you have a picture, A. You want a region of that picture. You want to create an image that represents a rectangle from 1010 to 100, and this is how you do it. You pass in a rectangle. You give you a region of interest. Okay, and you can also do something similar using a range object. Here, basically, range all means this is like take all this thing in the rows, and then I'm not sure whether it's a row or column. Sometimes I get confused. Row and columns get confused very easily because it's not quite intuitive like the way you think about it in X and Y. Because sometimes X means row. Sometimes I mean just anyway. When you in doubt, print it out. Take a look, because I get confused a lot of time. And here, basically, if you want to actually get another copy of this thing, you have to do an a.clone, or you can do a copy too, which is another way of doing it. So all this part of the code, you basically can get it from the OpenCV.org. There's a lot of tutorial. You can basically look at this. Okay.
Okay, real quick. On the line mat D, A comma, that's basically creating a match but of a reduced size.
Yes. Okay. Yes. So this actually, in contrast to Java, when you write this, when you declare this way, you actually create an object already. In Java, this is a null pointer exceptions. Actually, this probably doesn't even work here. Basically, you have to say mat D equal to new mat parentheses this. So anyway, I know 20th century C++. The 21st century C++ is very, very different. Let me put it that way. Data structure is almost the same as class. You can do almost everything in data structures. The structure class type. Structure in the class is almost like anomalous. We're going to talk a little bit on filtering. So as you guys already know, because you press WE, most of the so what the low pass filter is, right? So in the I don't have to explain to you in the regular electronic signal, but what about in graphics? When you have a low pass filter, what does that mean? So basically, when you have something that have a lot of texture, you have basically a lot of high frequency content. When you have like a flat color, that usually means that's a very low frequency. So when you do a low pass filter on an image, basically what you're doing is that you're blurring the edges, and any kind of noise will be sort of averaged out, or replaced by some sort of consensus values of the neighboring images. Okay. So this part here I just kind of copy, kind of paste. I ran out of time to kind of paraphrase them, but you can kind of see there's quite a lot of default values here you're not specified. And in order to understand fully what they do, you have to kind of read the API or read the paper to know why. And so the basic operation is very simple. Basically, you pass in the matrix that you want to blur, and you get something out. Okay, and this means reference for the people that are familiar with C++ or C. So if you want, so most of the time you can basically perform something that not in place. Means that you got a matrix coming in, you basically specify another matrix out. So these two matrices are two different things. But you can also say, okay, I want to blur, but I want to store in the same matrix. So you can pass in the same thing. Okay. So even though they say source and des, you can actually use the destinations. So we're going to talk about just two types of filtering here. One is the Gaussian blur, one is the blur. And I'll talk a little bit bilateral, but the example that I used did not kind of show the advantage of this. But this is kind of new thing. The bilateral is actually pretty new. It's like 2004 paper. So anyway, that's a good tutorial at MIT that talks about bilateral. So if you look online, Google for it, you see. So let me just look at the code for the low pass filter. So some of this code looks kind of boring because they're kind of doing the same thing, because you just read the image in and put some kind of salt and pepper onto the image just to simulate the noise. So this method here, salt, basically simulate the noise level. This is actually taken out from that book, the OpenCV 2 Practical Computing. It has talks a little bit on that. I changed the code slightly to make it easier to read. So basically, what it does is that it randomly puts some bright spot in your pictures. I mean, you can also choose a black spot in the picture so that you can see how well the filter works. So the first part of the code, after loading the image, is put salt in the image so that you could simulate, you can figure out how well this filter works. Okay, otherwise how do you know how well it works, right? So the first operation that we perform is blur. Okay, and the second one is Gaussian blur, and then the third one is bilateral filter. So this if you look at it, there's a tons of filtering operations in OpenCV for various reasons. The reason is because you probably need different things for different environments. Certain thing may work better for certain cases. So just run the code. Need images. So let's see. Okay. So the original picture, this is actually not original. I added the pattern, the salt noise to it already. Salt is white, pepper is black, so I don't add the pepper. You can actually add the pepper. So you can see that they did pretty well, right? Most of them. The blur operator, you see, you kind of clean it up, right? And then you see this Gaussian blur. They did pretty well too, right? So a Gaussian blur is basically like a bell-shaped curve, When you blur the stuff, it actually uses a way that look like a bell shape, like a Gaussian distributions. For those people who know statistics. So you see they did pretty well, right? All of them. But if you look at bilateral filtering, you actually preserve the edge better. You can see the nose looks a little bit, there's some textures here. This picture probably doesn't do a lot of justice, but if you look at some other literature, it talks about this. The reason is because you need to preserve the edge when you do the blurring and get rid of all the noise so that the noise doesn't impact your edge detection and things like that. But you don't want to throw all these edge away. The real edges, you want to preserve that as much as you can. Okay, that's the reason why you need to work with different filters. Any questions? I mean, this process is pretty straightforward, really.
So all those libraries are already in OpenCV?
Yeah, the 500 functions that I talked about
Wow.
earlier. The CVT : CV : blur. CV
So you don't have to do all the math. You don't need to know all the math.
You don't need to.
Okay.
This is why I kind of motivate by looking at the calculator example earlier, so that you can kind of see how difficult it is to do some of the stuff yourself, or how easy it is. Depends on your viewpoint.
Then again, you get too dependent on libraries, then you're limited to just what the libraries allow you to do.
Yeah, but as the library get better, things change, and OpenCV, will probably change some of these in the next 10 years that you probably don't have to know any of these. But I think I heard that before. Now we just look at the low pass filter. So now we'll look at the high pass filter, which is basically doing the opposite to that. So this one basically want to attenuate the high frequency signal, and basically I'm sorry, I said emphasize the high frequency and attenuate the low frequency signal. Okay. So the code is basically the same thing, except that in this case you have this Sobel. I actually don't know how to pronounce this. Anybody know how to pronounce this?
Sobel?
Sobel.
Sobel.
Sobel. Okay. It's somebody's last name. Okay.
Yeah.
So yeah, so the Sobel operator. You basically have two parts. You have the Sobel x and Sobel y, because you're kind of taking the derivative along the x directions and derivative on the y directions, and then you can combine them. So so you can basically add the x and y directions by using this operation here. You see the overloaded operation I talked about earlier.
Mm-hmm.
You want to add two images, you just do this, something x plus something y.
Okay.
See? Otherwise, you have to write whole bunch of for loops to do all those things that you're talking about. It needs 20 lines of code to do that.
Are you taking the absolute value? Is that what that
Yes,
would be? Yes.
the absolute value is also overloaded.
Okay.
Everything here is overloaded. Because when you say absolute, it actually goes through another for loop to clean up the thing. And the reason why we need absolute value is because if you don't, they'll just cancel out sometimes, because you have one positive, one negative derivative, but they're all
Mhm.
indication of some kind of gradient, but you don't want to cancel it. And after that, after we get the Sobel results, then we basically threshold it so that you can kind of see the line from the picture.
Now, does this Sobel here, do they have a means of getting, in a raw Sobel, you get two pieces of information you can get out of it. One is amplitude, and second is compass.
Yeah, you can also figure out where you basically figure out the magnitude based on x and y. You can also figure out the tangent, the arctangent of it, which is basically the directions.
Okay.
Yeah, you can get it, all these things. I mean,
Yeah.
that stuff is pretty straightforward. It's in the tutorial somewhere, but it's very long. I mean, the reason why I didn't include that is because that just...
Well, right now, people are more interested in amplitude than compass.
Yeah, because the thing is that it all depends on what you want to do next.
Sure.
If you just want to know that there's some bump there, in the picture,
Yeah.
so that you can get sort of contouring or whatever, then you don't need to know what direction it is. But let's say you want to know whether it's a corner or the window, then you need to know which direction it is, whether they are from. When you have a corner, the derivative actually is kind of diagonal in all directions. So that's how you can tell whether it's corner versus just the edge over.
Yeah, I used to use that method.
You know what?
Yeah.
Just by a question I know you're using. Next one we're going to use is the Laplacian, which is the second derivative. So one thing that you probably notice is that there's just a lot of math, and that's the nature of the beast.
Yeah, and what you're seeing here does not show you near the amount of floating point operations that are really going on when you do one of these commands. There's literally probably 16, for every pixel in the image you're looking at, and you do a Sobel across the whole image, there's going to be at least 16 floating point operations per pixel. Multiply that by the size of your resolution. That's a lot of flops.
I guess that's what MATLAB did when you passed the matrix. Because that's what we did, we compared them.
Yeah.
And you would also use that. So OpenCV is also for animation. So you can actually rotate it based on how you manipulate the matrix.
Is that easy to find out the color of the pixel?
It's easy. You can just use a dot add. I didn't show it here, but I actually kind of show it just how to set it earlier in the salt and pepper example, in the low pass case. In the low pass filter case where I have this method here, you see here, I have two ways of basically setting the value. You can do the add, or you can just use this thing, this kind of neat thing.
That's a set that I'm saying.
So you can do the same thing. Set, it's the same thing basically. Just basically set basically this is setting, right? You said getting?
Yeah, I have an image. I
Yeah,
want
just
to get the
IJ.
picture.
Just IJ and stuff. I can show it later. But I don't have anything that here that because when we play stuff, sometimes we just want to do it in row using kernel, go through the stuff. So there's all